Hello my dears, how are you all? So for a few days we didn't put any classes there in the our normal lecture series, because we have started a new series for previous year question paper solving. So and almost we completed 70 to 80% of the syllabus regarding every examination, right? Machine, circuit theory, measurements, power system, everything we completed. Basic electrical especially we all completed, and some portion of electronics, some portion of power system only we have to complete, we have to finish. So meanwhile I will take that also, and please do watch this lecture series also, because this is the foundation, this is the basic, and don't go directly to the previous year question paper. If you have a strong base, then you can go there, no problem. But if you don't have a base, please watch the playlist, that is our this lecture series continuously, and then only you can switch to the previous year question paper answering and all. Okay, if you have a base, then go there and go here, and you can play anywhere, no problem. But if you don't have, then please continue to watch this, because this is very important. If your fundamental theory is very strong enough, then you can solve any questions, right? Or you can actually at least try any question, even though if you can't solve until the answer get, but you can try at least. So that level you will get if you completely get the basic knowledge, right? So today we are going to discuss another important topic in the KSEB sub-engineer examination, and for all examination, it is nothing but optoelectronic devices. It is nothing but optoelectronic devices. Optoelectronics devices. So what is mean by optoelectronic devices? So optoelectronic devices are nothing but a device which can convert light energy into electrical energy, or electrical energy into light energy, anything. That any conversion is possible in optoelectronic devices. For example, LED. LED is an optoelectronic device because it converts the current that or electrical energy to light energy. Photodiode, it is a reverse case actually. If you give light energy, it will convert it into electrical energy. Laser, it is also an optoelectronic device, because we are giving electrical energy, the output will be in the form of a light. So optoelectronic devices are nothing but those devices which convert light energy into electrical energy, or vice versa. That is called the optoelectronic devices. So first of all, we have to study about a very important optoelectronic devices, which is nothing but the solar cell, which is nothing but the solar cell. Okay, so solar cell means it is nothing but simply it is a PN junction diode. It is a PN junction diode. Solar cell is also a PN junction diode, and which is made up of material like germanium, silicon, gallium arsenide, or cadmium, tellurium, etc. So these are the material which we are normally used to make for the solar cell. Okay, and this is the construction of the solar cell, my dear. This is the construction diagram of a solar cell. Okay, so actually the solar cell is constructed by, it is not exactly equal to a PN junction diode, because in PN junction diode both P and N regions are equal width and equal thickness, right? But in the solar cell, how we are making a solar cell means we are allowed to grow a small or a thin layer of N type, a thin layer of N type semiconductor on a thick layer of P type semiconductor. That is how we have to make the basic basement of the our solar cell. Okay, a thin layer of N type material is allowed to grow on a thick layer of P type semiconductor. So finally this structure will be like this, and the top of the N and the bottom of the P, we are making two electrodes for the external connection. Either you can connect the load here, or you can connect the load here, no problem. And how this works, it's very interesting actually. See, as soon as this PN junction formed, as soon as this PN junction we sandwiched together, of course, as like in PN junction diode, here also there is a depletion layer formation. Here also there is a depletion layer formation, and we know that depletion layer is nothing but it is a region at which electrons and hole recombined together. There is no mobile charges. That is why it is called a depletion layer, because the region is not allowed to flow any type of charge carriers there, because that is why it is called a depletion. It is depleted of charge carriers. It is depleted of charge carrier, or in other words, there is a recombined state of electron and hole we can see, right? There is a recombined state of electron and hole we can see. And what happened when photon is allowed to fall on this depletion layer? Actually, the whole structure now, this P and N, the whole structure is encapsulated with, encapsulated means simply covered with a glass or a thick optical material, so that the light can enter into this structure, but the dust and the humid and the external disturbance does not affect the total structure. That is why we have to encapsulate the whole system with some material like a glass. Normally it is glass actually. So that you can see in the solar cell panel na? The solar cell panel, you can see the reflection na? Your reflection you can see, that is glass. So inside that glass is actually the p-n junction diode. Okay, so come to the point. So what happened when photon having sufficient amount of energy? The photon should have a sufficient amount of energy, right? Because when we are on our torch and allowed to apply on the solar cell, it will not produce any electrical energy. That means the incident ray should have certain amount of photon energy, right? So if the photon absorbed, it have a sufficient amount of energy, and that too which strikes on this depletion region, the photons are allowed to strike on the depletion region. And this is, you have to note one important thing here, that the photons are allowed to strike on the depletion region, not on N region, not on P region, but on the N region, on the depletion region. So the photons are allowed to strike on this depletion region. And what happens, my dear, what happened there? Because the depletion region is nothing but what? A region containing electron and hole recombined state. Whenever the light falls on the depletion region, what happened? The electrons and holes now, that combined state, right? Combined state, it will release. That means the combined state will break. The electron and hole combined state is actually there in the depletion region. That's why it is called a depletion region. It is depleted of carriers. It is depleted of carriers, which doesn't mean that there is no charge carriers as it is, but there is a charge carriers, but it is in recombined form. That's the difference. So here also charge carriers, but these are in the recombined state. So what happened when the light strike? The recombined electrons and hole now, it will what? Break their bond. They will break their bond, and electrons and hole separated. So what happened here? The electrons and holes now, here inside that electrons and hole generated, and you might have think that this electron can easily come to the hole, P region here, and they will recombine again. No, that won't happen, because even though they're inside these, the electrons and holes are generated, this is a very big barrier actually. The barrier, they doesn't want to, it doesn't allow the electrons to come from this to this region. But what happened? It is very easy to move the electron towards the N itself and holes towards the P itself. That is the difference you have to note down here. Because whenever the electrons and hole generated, the electron will not go to P directly inside the cell, and the holes directly go to N region inside the cell. Because of the barrier, because of the potential barrier there, the barrier doesn't allow to go the electrons here and hole to here. That means the barrier is not breaking. How can we combine this electron and holes in the P region? Only by breaking the barrier. But now whenever the light strikes on the potential region, the barrier is not breaking. The potential barrier is not breaking, but electrons and holes generate only. Barrier, if the barrier is only breaking, then only the electrons from this combined with holes from the P region. That is how the barrier breakage and the conduction inside the cell happens. It like the PN junction diode now, if we are applying a forward biasing, what happened? The barrier is breaking and the crossing of electron and holes taking place. That's how the barrier is breaking, because that much energy we are externally we are providing. But here it is different. That is why I am emphasizing more and more here, because now we are applying an electrical energy in the photon energy in the barrier. The barrier is not breaking now, but instead of that, electrons and hole pairs will be generated. That electron will come to this N region, holes will come to this P region, not crossing, because barrier is still there. You have to think and you have to imagine, then only you will get the idea. So what happened? Electron will move here and hole will move here. Is it correct? And if the photon is continuously absorbing here in the depletion region, sufficient amount of electrons will be here in the N region and sufficient amount of holes will be here in the P region. So it is like a battery. See, battery means what? Some electrons will be there. Battery, how the battery work? There will be some electrons and there will be some positive charge in the bottom. So there will be a potential difference, so that the current will be flow from here to here, right? Correct now. So here also like that, the electrons will be accumulated here, the holes will be accumulated here. So if we connect an external load here, what happen? Through the load, the current will start flowing. Through the load, the current will start flowing. That means there you created a potential difference from the top to bottom, so that the electrons will move from here to here and the current will be in opposite now, because the opposite direction of electron will be the current. So this will be the current direction. Correct now. And that electron, right, that electron come here and combined with the hole here, combined with the holes in the P region, and electron hole recombination takes place. Correct? Is it correct? And again the photon comes, the depletion layer, generate more and more electron. Again that electron will come here and electron hole combination take place. Now these hole combined electrons, now this electron hole combination takes place. Now this will slowly come here and again come to here. Again the photon strike, it will liberate energy, it will break the electron hole pair. Again the process continue. That is why a solar cell lasts for 25 to 30 years now. It will not damage at all. It will not stop its conduction at all, because more and more electrons are generating continuously. Only to generate there is a force needed, that force is supplied by the photon. That is only the difference. But otherwise there is continuously the production of electrons and holes in the depletion region, and the depletion region never going to break down. Only the depletion regions always exist there to maintain the potential. Then only there will be potential difference between the top N layer and the bottom P layer. Otherwise there will not be any potential. If it crosses automatically, then how the conduction doesn't take place through the external circuit, right? The conduction takes place through the internal circuit only, like PN junction diode. We want it is act like a solar cell. So if you want it is act like a battery, then the potential difference should be there. Clear? That making potential difference by the depletion layer. Is it clear, my dear? So that is the simple working of the solar cell. I hope you understood everything, right? And this is the characteristics. And this is the characteristics, means simply nothing but the voltage, PV voltage. And this effect na generation of or the making of some potential difference from top to bottom is called the photovoltaic effect. So this is very important term. Photovoltaic effect is nothing but making a potential difference, and there hence you allow to flow a current in the external circuitry by giving some photon energy to the depletion region of a PN junction diode is called the photovoltaic effect. Is called the photovoltaic effect. And this is the characteristics, my dear. The characteristics simply shows this is the voltage and this is the PV current, photovoltaic voltage and photovoltaic current, and this is called the short circuit voltage. Short circuit voltage, that is the maximum voltage. Okay, sorry, open circuit voltage, not the short circuit, open circuit voltage. Maximum voltage when it is in open circuit condition. Open circuit voltage, and this is nothing but the short circuit current. Short circuit current. Short circuit current is nothing but simply you have to short circuit, instead of load simply you have to connect the two external electrodes via a conductor, so that maximum current will be flowing there. That is why there is a 5 ampere. Suppose you imagine there is a 5 ampere current, and that is called the short circuit current. The same manner, if you open circuit this load, means you will get a maximum voltage across the terminal. That is called the open circuit voltage. And none of these two regions it is not suitable for working, because either the open circuit is not in our cup of tea, or a short circuit current is not our cup of tea. Our load is in between these two now. Either open circuit and short circuit. In between these two regions our load will exist actually. So we always prefer a good point for working of the solar cell, which is called the maximum power point, and that is nothing but this region. Okay, that is actually, so many calculations are there in order to calculate the maximum power point, because open circuit voltage here the current is 0. Short circuit current the voltage is 0. Then how can we get a maximum power, maximum voltage into maximum current? Not the open circuit voltage, because at that time current is 0. Not the short circuit current, because at that time voltage is 0. So we have to generate an algorithm, or we have to generate some calculation in order to know which region or which point in the characteristics curve actually implies what? A maximum power point. That is nothing but this curve. Okay, just you have to know the basic, that's all, nothing more, nothing less. Okay, is it clear, my dears? Is it clear? So that's all about the what solar cell, my dears. So now we are going to discuss about LED. So LED is nothing but light emitting diode. This is also an optoelectronic device which can emit light if you are giving electrical energy to the PN junction. Okay, and let's see how it is working actually. See, LED is nothing but a forward biased PN junction diode. That is a very important point you have to note. It is a forward biased PN junction diode. Okay, PN junction diode. Okay, so normally the material used here, not pure silicon or not pure germanium, but instead of that we are using gallium arsenide. Okay, or gallium phosphate. So these are the material we are commonly used here, and I will tell you why, the reason. Okay, now, and see how it is working actually. This is a normally PN junction diode, my dear. If you allow the PN junction diode to be in forward biased condition, what happen? These electrons will be attracted by this positive polarity, and it will come across the junction, and it will combine with the holes in the what? P region, so that the electron hole recombination will take place. Electron hole recombination will take place. And what happen if electrons and hole recombine? Light will emit. And already told you that not pure silicon or pure germanium is not used, because in pure germanium or silicon, if you allowed to strike the electron and hole together and their recombination, if you allow their recombination, visible region light energy that will not produce. Even though there is a small light produced when the recombination happen, because lot of energy is converting there, right? The striking means the energy conversion. So that energy conversion is visible in the range, or visible by seen as a light wave. But in pure silicon or in pure germanium, we can't see the light wave. Is it clear? So what we have to do, we have to modify the material. Anyway, we have to use semiconductors now. So gallium arsenide is a combination of material, gallium and arsenide. Gallium phosphate is a combination of material. So these combinations of material normally we are using for making the LED, so that we can see the light in very intense form. Either we are using gas and gallium arsenide. This will produce normally the red light, and this will produce normally the green light. And by adjusting the percentage of this material, gallium arsenide, that combination percentage, you can vary the color of the LED. Is it clear? So simply, which is nothing but LED means light emitting diode. How the light will emit when it is recombined together, electrons and hole combination happens, the light will emit. That's all. Is it clear? And normally you have to see this range of wavelength for visible light, okay, ultraviolet and infrared region. Okay, so for visible light, visible 450 nanometer to 700 nanometer. For IR, it is 700 nanometer to 10 raised to 5 nanometer. And for UV, it is 1 nanometer to 450 nanometer. This is very important because in normally many of the examination I have seen this region, visible region wavelength is what? Many of the examination I have seen. So this point you have to note, it is in the range of 450 to 750, 700 nanometer is the range of what? Range of region, right? Range of wavelength, actually range of wavelength. So that you have to note. So that's all about the LED. Okay, that's all about the LED. Nothing. This is the symbol. You have to make sure that the arrow should be in that is towards us actually, or away from the PN junction. The arrow should be away from the PN junction. That only you have to take care. Okay, otherwise it's same. Okay, no problem. So that's all about the light emitting diode. Is it clear, my dears? So let's move on to another optoelectronic devices, that is nothing but photodiode. So now you have to see what is meant by a photodiode. Okay, photodiode means important thing you have to note. It is a reverse biased PN junction diode. That's all. That is the very important point, or the examiner will ask these type of points actually. And the symbol is nothing but, my dear, it's normally like a PN junction diode. Okay, it is normally like a PN junction diode, but the arrow should be in opposite manner. It is normally like a PN junction diode, so the arrow should be like this. The arrow should be towards the PN junction diode. That is the symbol. This is anode and this is cathode. Okay, anode and cathode. And normally the material used is germanium or silicon. No problem, you can use any material for making the photodiode. But the thing is that it is a reverse biased diode. That's the only difference. Okay, it is the reverse biased diode. And let's see a small construction detail now. So this is the PN junction diode, am I right? So this is the reverse biased condition. This is the reverse biased condition. So whenever there is a reverse biased condition, there will be a depletion layer, am I right? There will be a depletion layer formation. So this is our depletion layer. This is our depletion layer. This is our depletion layer. And photodiode means it changes its resistance when light fall on it, right? It changes its resistance when light fall on it. So what happens, see, whenever we are giving some light energy to the junction, to the reverse biased junction, whenever we allow to fall some light, what happens here? There also a new electron hole recombination will take place, and electrons, here the electrons now, here than the material used in the solar cell are different, because here we are biasing. Here we are biasing already, but there is no biasing in the solar cell. That's why the difference, I will tell you now. So when the light hits on the depletion region, electrons and hole recombined state now, that is why it is called a depletion region. The electrons and hole will release. The electron and hole will break their bond. The combined bond now that will break, and electrons and holes will be free to move now. So what happened? The electrons, the holes in a hole, the hole will move to this electronic, this n region, that is a negative potential, and the electrons will move towards the positive direction. Is it clear? In the solar cell there were no biasing. That is why it doesn't move externally, but it move only what? Electrons will move directly to n, holes will move directly to p. But in the case of here, we biased externally, so holes will move here and combined here. Electrons will move here and combine here, that's all. Is it clear? So whenever light intensity is very high means the depletion region liberate more and more energy, the current will be flowing like this. The current will be flowing like this. Okay, the holes will come here now, so the current will be flowing like this. The current will be flowing like this. Okay, so it is the reverse biased PN junction diode. That is the only difference. And there are two type of current there. First one is called the dark current, and second one is called light current. Light current. So the dark current is nothing but no light. That means a small leakage current will be always flowing whenever a PN junction diode is in reverse biased condition due to minority carrier. That is called the dark current. And light current is nothing but when light is there. Whenever there is a light on the PN junction diode, the current is called the light current. So the total current is always the sum of the dark current plus the light current. And we can increase the sensitivity of the PN junction diode or the photodiode by reducing the dark current, so that we can clearly visible or we can clearly see how much light current is there. If the dark current is very high, we can't distinguish the light current and dark current when light falls. So by reducing the dark current so much low value, we can increase the sensitivity of the photodiode. We can increase the sensitivity. Okay, so that's all about the photodiode, my dear. For examination point of view, this is more than sufficient.